All right, good morning, everyone. So you all know me, right? I'm Jason Bakos. You all had me for 611, right? Good. This is 491 Capstone Computer Engineering Project. We have it. We recently changed this prerequisites to 240, 313, and 611. So you all should be seniors. This should, I think, most of your last semester, all of you guys. Okay. So we're meeting here Tuesdays and Thursdays, 10:05 to 11:20. So we don't have separate lectures in lab like we did in 611, unfortunately. So I have to lecture in this room, which is awful. But the nice thing is that we can do ad hoc lectures, right? So we don't have to. We're not fixed to a specific schedule. I'm gonna start using Blackboard this semester. I used to use Moodle, but that has now been banned. So we're using Blackboard. But I'll still put lecture recordings on my YouTube channel if you miss class or you want to hear something again. We're going to be using software installed in this lab and hardware in this lab. And then announcements will go out on your email.sc.edu account, so make sure you're checking that. And we'll be working in teams, and each team will have to find a way to collaborate, right? To share resources. There is a textbook. It's just a preliminary version. I've been working on it specifically for this class. It looks like this, and there's a link on there to get it. We have the course learning outcomes on there. We'll skip that. I've got important dates on there. We'll skip that. Teaching assistant is Soyash Singh. I think you all know him from 611. He's not here today, but he's in a story with me in the lab if you need help. And you can make an appointment with him to meet you down here. And we have the grading structure on there. So this is primarily a lab course. So most of the 41.2% of the grade will come from lab projects. I used to have all the grade come from lab projects, but there is a conceptual component of this course, which is the material that cannot be taught through labs. In this case, primarily the hardware design part of it. And then I have an approximate schedule there in section 9. Section 10 talks about if you need help with disabilities, what to do. Section 11 says that we may have to update the syllabus, but we'll let you know if we do that. 12 is the standard grading scale. 13 is the academic honesty policy. Obviously, teams have to share code, but you shouldn't share code or designs between teams. But you are welcome to help each other out with the tools, the CAD tools, the software tools, which can be tricky sometimes. That's why we're in the lab here together. Lab attendance is up to you, and I have the lectures, like I said, will be posted online. But in general, you may have to spend more time in here to get the projects done than we have allocated for class. Just keep that in mind. And I think 15 is the group work policy. Both members of each team will receive the same grade on all the group projects and all the lab projects, but keep in mind that's only accounts for 41% of the grade. The other part of the grade is individual. And then section 16 shows the policies for project submissions. They have to compile to receive partial credit. Only one member of each project group needs to submit the project online on Blackboard. But we'll also be doing demos, project demos, which is the next bullet. We have a cutoff date, which is reading day, I believe, is what we have listed there in the schedule. So you have to submit everything by reading day in order to get credit. Now the projects have due dates, but there's just a 5% penalty for each school day after the due date you upload it, and it's capped at 30%. So reading day is the day after finals week. Or day before finals week, sorry. Yeah, day before finals week. Basically the last day of the semester, but there's no classes on reading day. Syllabus? And you can only submit one version of each project. And that's because with the late penalty structure set up the way it is, we've had cases where students would submit multiple versions to try to get the best, optimize the grade. So we just want to grade once. Okay, any questions about the syllabus? All right. Okay, so what is this class all about? So we're going to cover embedded and cyberphysical systems and the design and testing of them. An embedded system is any kind of computer system that's designed for a specific purpose. You guys all took 313, which is about embedded systems, where you designed hardware, software on the FPGA boards, and obviously you optimize them for the specific purposes, in the case of rotating the image or generating the fractal, and you evaluated those. And a cyberphysical system is a type of embedded system that connects with sensors and actuators to interact with the physical world. So robots or self-driving cars or drones, that sort of stuff, right? So we designed this class about 5 years ago after we had our program was evaluated by the accreditation agency, ABET. So the computer engineering program was evaluated, and they said we needed more hands-on lab courses, laboratory classes, where you actually build stuff. So in response to that, we added Electrical 201, which you've all taken, right? So we took out electronics, Electrical 371, which all the computer engineering majors hated. We took that out, and we replaced it with 201, where you got a chance to build some stuff in the electrical engineering department. And then we built this lab. The college invested money in here. We bought the furniture and the oscilloscopes and the power supplies and soldering irons and all that stuff. But then, we had to figure out, well, what are we gonna build? What are we gonna do? So it just so happened that first semester was when the university shut down for COVID, and then the following spring, when we offered the course, we were all just at home, so we couldn't do any stuff. And meanwhile, this lab just gathered dust for a year, so we had to redesign the course a few times. And a lot of the conceptual material I cover in this semester comes from that COVID, time, where we covered a lot of concepts, and we left some of that in just because it's good to have that. Okay, so one of the things you have to keep in mind, and I'm sure you guys probably already know this by now, but just to be clear, there's different types of CPUs, and they're all on this trade-off space between because everyone wants the CPU, part of a system to be lightweight, right, low power and small, right? But there is this trade-off between performance and power and performance and footprint, right? And so there's this huge space of processor technologies, most of which are intended for embedded purposes, but they're all in different, sort of places on this spectrum. So you can go all the way from really lightweight processors that, play a song when you open a greeting card, up until these kind of embedded processors that, be in a glasses or a watch or a action cam, all the way up to like an embedded system in a Tesla, which is probably the highest end you can get without being like a server processor, right? So when we're developing this class, we've made a few changes. We keep having to decide where we want to be on this spectrum. And so when we first started out, the first time we taught it, we were using these Arduino boards. I think you guys probably used Arduinos a little bit in 211, right? And so the quintessential Arduino processor is the Atmel ATmega 328, which is an 8-bit processor. And it's kind of crazy, like when you think about there being 8-bit processors in 2025. It's amazing that they even exist still, but yet not only do they exist, but they're still wildly popular. And the reason is because they're cheap. And for a lot of applications, they can still get the job done, right? The problem is that they are really chintzy even for this type of environment. I mean, it's like the size of a credit card. They're real flimsy. right? And they can't really do that much, right? So we started out with those. In fact, you can still, even to this day, because no one cleaned them up, you can still see, even though this was 5 years ago, this was the kit that we used to give out. And we have the boards in here and all the peripherals. And then we had this white programmer. So we used to actually program the firmware. So we programmed them at a low level instead of using the Arduino IDE that you might be familiar with. We would flash the firmware and program them that way. And then, as I mentioned, we took basically a year off and taught this course online. It was just kind of a traditional course. And then when we came back, I didn't really like these Arduinos very much. It just was, it was too much work for such a little payoff. I mean, we'd spend like weeks to try to get it to blink a light. You'd have to plug the stuff in the breadboard, and you'd have to, fool with the debugger. You couldn't just plug a USB in. You had to go through the debugger. So it was, I didn't like it. So for the next 3 years or so, we actually were using the FPGA boards from 611 and 313. I thought, well, this is a really efficient use of this hardware because we can use it for 3 classes. And that way I can also check off some things on my bucket list, which was to combine 611 and 313, where you get to design an IP block using System Verilog and then put it inside the 313 system on chip architecture, connect it with the Neos processor, which is a 32-bit processor, much more powerful than the Atmel processor. And it has debugging support, so you can step through your code. It's really nice. And so we did that for a few years. But the problem was, in terms of what we could actually do with it, there wasn't much we can do. I mean, basically in the end, we just made a clock by the end of the semester. We connected to a DC motor and we controlled the second hand. And so for a while, I've been looking for something a little bit more exciting, right? And so I think we finally came up with it. And Alex, do you want to show that? This is kind of a cool project. And I don't know if we'll actually get to this, but I think it's a nice end goal. So what this is a cube, obviously, but it has 3 internal motors in it that when you turn it on, and the motors are connected to wheels with weights on them. So when the motors spin, it puts a torque on there, and the thing can actually balance on one of the points of the cube, right? So it has this control. It has a closed loop control algorithm in there that keeps it balanced. But in order to build something like that, you have to have a processor that's capable of running it, and then you have to have enough peripherals. They have to be able to control 3 motors, which requires a lot of pins, more pins than I think we had on that guy. And it also has to have pins you have to be able to read the accelerometer, to be able to, to measure the state of the cube. And then there's other things attached to it too, like there's a buzzer, and then it has a console where you can interact with it and tune the controller. And there's a whole bunch of stuff that goes into that. So our idea was to move away from the FPGA and switch to this ESP32, which is a lot more powerful than this guy. So this is a 32-bit processor, multi-core. Instead of 16 megahertz like that thing ran at, I think it's hundreds of megahertz, 240 megahertz. So it's probably 10 times as powerful as that one, if not more. Also, it has Wi-Fi and Bluetooth built in. That's kind of what the ESP32 was originally kind of positioned for, was the wireless capabilities. And then the other issue was this board. I always hated these little dinky boards. So with the help of Alex, we have custom boards for this class. These are custom, I don't know what you call them, like carrier boards, essentially. So you take the ESP32 module and you put it into this carrier board, and it kind of breaks it out, and then we have peripherals. So this is kind of analogous to the FPGA boards that we use in 611 and 313. Not as big, and there's not as many things on it, but the things that we do have on it are specifically designed to work towards getting something like that cube working. So basically, this is a test board for the components that would have to go into that cube, right? And it allows us to write code and evaluate the different peripherals independently before eventually, hopefully, putting everything together and having it run, having it balance on that cube. Does that make sense? Right? So these are bespoke boards specifically for this class and specifically for the projects for this class. Now, if we get to the end, and I don't know how far we're going to get because this is the first time we've done it this way, ideally, we're going to give you these boards to develop some of the initial projects on, and then eventually you guys will design your own board for the cube. But again, I don't know exactly how the schedule is going to work out for the class, right? Does it make sense? So we're going to have a mixture of lectures where I'll sort of, act like we're in a vocational school, and I'll just tell you essentially how to program the ESP32, but that will be mixed in with some conceptual stuff, right, about embedded systems. And then there's the hardware part. So once you switch from the FPGA to this type of fixed architecture, you can't really do any hardware design anymore, aside from designing the board. So the nice thing about using the FPGA was we're able to design our own pulse width modulator circuit that we use. That was how one of the projects we used to have in this class. We can no longer do that. We have to use the PWM circuit that they give us, that Expressivs gives us on here. But we'll still cover a lot of that hardware design stuff in the lectures, right? And then, of course, we'll have some quizzes and exams on that. So it's kind of more of the traditional part of the class, right? And at the same time, we'll be working on projects with this. Does that make sense? You guys with me? So I don't know, this will be a little, you'll have to bear with us. It'll be a little experimental. Okay, so topics-wise, to me, there's four main topics for embedded systems and cyber-physical systems. Probably the biggest one is hardware-software interfacing. This is something that you guys don't really get much of a chance to do in our curriculum. When you start out, you take 145, 146, 240, 245, 311. In fact, every programming class you take, you do I/O, but you do it through, just standard libraries, right? You never really think about how hardware and software communicates. And that was something that, when I was in undergraduate school, it kind of bugged me because I didn't, we never really got to, my dream was to write a driver, for Linux. That was my dream when I was 18, because it was like, that was arcane knowledge that no one knew and no one taught in any university, right? So that was something that and it's highly relevant when you're designing embedded systems because, because you're designing a specialized system and there's a lot of interactivity between the processor and hardware, right? Obviously, because you got to talk to sensors and actuators. And then there's system on chip design. This was part that we took out. So in the previous version of this class, we had a system Verilog module. We put it inside of a system on chip, and you had to learn how to create an Avalon slave, component. We took that out, but we'll still talk about that. And then control theory is another topic that you don't see at all in computer science. You have the option to take Electrical 331, which is the control theory class in electrical engineering, and you can count that as an elective, but in 20 years, I've never seen a computer engineering student actually take that class. And so, because it's basically the way they teach it in the electrical is a math class, right? In this class, I'm going to teach a little bit of control theory in a more applied way. Actually, you do cover a little bit in robotics, I guess. You do some basic, PID controller stuff in robotics, but you don't cover. I'm going to get a little bit more into the theory of control system, and we'll talk about S domain, Z domain, and state space control systems a little bit. So we'll cover that, and then real-time scheduling, which is is a big deal, and I think that's probably the first time you've seen that. So the idea is that when you have one of these processors, it's going to be controlling multiple things in parallel, and if you keep adding tasks for the processor, eventually it will fail to be able to meet all of its real-time deadlines. It'll fail to keep up. It has to keep up with the physical world, right? But eventually, as you keep adding tasks to it, the utilization will hit 100%, and you'll no longer be able to keep up, at which point you have to buy a faster processor. And this is the reason why if you look inside of a Tesla, they have really fast CPUs in there. You might say, why not just run a Tesla off an Arduino? What's the problem, Elon? Well, the problem is it doesn't have the capabilities to keep up with all the code it has to run and hit all the deadlines it has to meet in order to process the workload and keep up with the physical, road as it drives down the road, right? That's why Tesla has invested all this money in building these custom processors for the assisted automated driver's assistance systems. So that's something we want to address and talk about that. So we're going to start out talking about hardware-software interfacing. So there's two perspectives for this. One is from the software side. So what does the software look like that talks to hardware? And then there's also the hardware side. What is the hardware doing? So from the software side, there's basically just three mechanisms by which software talks to hardware. There's programmed I/O, interrupts, and direct memory access, and that's been true for about 60 years. It's just, that's the same three methods that they've been using since Apollo 11. That's the only way to do it. And then there's the hardware perspective, which are the physical protocols, the signaling protocols that are used, and there is a ton of those. Right? Now, obviously, we can't design physical circuits that talk to other circuits across the wire because we don't have control over the hardware anymore. But one thing we can do is we can use something called bit banging, if you've ever heard of that, which is where you write software to implement these protocols directly, like you drive the protocols from software. Now, no one ever does that. In reality, these protocols are driven by specialized circuits. Driving a protocol directly from software is a very inefficient use of the CPU, which is why on these chips, these embedded chips, they have hardware to do that. But the bit banging it serves as a valuable educational tool so you can learn how the protocol works. You guys with me? So that's not something, it's not very practical, but it's good from an educational sense, especially when we don't have system Verilog and FPGAs and you can't actually implement the hardware. So what is programmed I/O? So this is the thing that used to bug me when I was an undergraduate student. I would take an architecture course, and they said, okay, there's three types of instructions that a CPU can execute. First of all, the only thing a CPU can do is execute instructions, and there's three types of instructions. There's arithmetic, logical, shift, and comparison, which are your number crunching instructions, right? Your computational instructions. Then you've got your control instructions, branch and jumps, that control the flow of instruction flow, which is for, implements, if statements, and loops, right? And then you got loads and stores, and that's it. And I was like, I think you're forgetting one. If that's all a CPU can do, how does it talk to the outside world? How does it do I/O? And they're like, at the time, unclear. We don't teach that. It's like, how do I print something on the screen if I can only do arithmetic instructions, shift control instructions, and load and store? How does that work? So as it turns out, it's not obvious, but all I/O is done through load and store instructions. But the problem is when you learn about those in architecture, the way they're defined is that a load and store instruction transfers data between registers and memory. That's the way they're defined, right? If you want to take data in a register and put it in RAM, use a store. And if you want to take data from RAM and put it in a register, use a load, right? So how does that work with I/O or communicating with other? How does the CPU use that to communicate with external circuits, peripherals? The way it does it is through special addresses, magic numbers. So if you store or load from specific ranges of addresses in the hardware, in the hardware that the CPU sits in, like in the system the CPU sits in, those loads and stores are intercepted and they don't go to memory, right? They're short-circuited, and instead of going to memory, they go to peripherals, and they allow you to access control and status registers. Now, a control and status register is just a little area inside of a peripheral that you can write to or read from with a load or store instruction to either read the status register or to control the peripheral. That's why they call them. Now that terminology is a little out of date. No one calls them control and status registers anymore, it seems. It's still, but that's, and they're basically the same thing. The only difference is a control register is something you're supposed to write to, and a status register is something you're supposed to read from, right? So control is an output, status is an input. But in reality, a lot of these registers are actually mixed. They're comprised of different parts that some parts are read and some parts are written, right? They're not necessarily the whole register is output or input. You guys with me? But I still call them control and status registers because I don't know what else call them. So what you end up with is, and this is true, by the way, of CPU processors and server processors and laptop processors and tablet processors and cell phone processors and embedded processors. They all work this way. You have these magic addresses. Now the question is, how does Linux know what these magic addresses are? Well, it knows this through something called the device tree, which is part of the boot up process when you boot Linux. It reads in the device tree, and the device tree has all these addresses listed in it, and you can actually change them. You can go in and you can change the addresses. But the problem is that these addresses None of these can be changed. They're all baked into the hardware. There's no way to change, unless you're on an FPGA. Like when you guys took 313, you were actually able to change these addresses associated with the peripherals because you were able to design the hardware. But if you have a fixed hardware system, like an ESP32 or an Arduino or an Intel processor, these guys are not changeable, right? Now, when you're programming in an operating system with a virtual memory, you don't see these addresses because you're not using, these addresses are all physical addresses. When you use an embedded system like the ESP32 or the Arduino, you can directly access these addresses with your user code, right? You're not blocked from it from the operating system like you would if you had an operating system like Linux. You guys with me? Okay. So anyway, so for example, you'll have a chip. Inside that chip, you'll have a CPU, and then there's some kind of an interconnect. And this interconnect implements some kind of an on-chip interconnect between the CPU and the peripherals. This is usually a jealously guarded secret. For example, we have no idea how the interconnect works on an ESP32. They'll never tell you that. On the FPGAs that we use, we knew it was the Avalon bus or the Axie bus, right? But we don't know what the interconnect looks like. It's just vague. But it's something that will monitor the CPU's load and store interface, and it will intercept instead of sending certain addresses to memory, to RAM, it'll intercept and send them to certain peripherals based on the address. So in other words, the address that you're loading from or storing to is acting like an address for a specific peripheral. You guys with me? So you end up with this address map or an address space. So for example, I may have an SPI peripheral. SPI is in a protocol, like it's like a bridge, like it's a way to get out of the chip. It's a language that I can use to speak to other chips, SPI. And that SPI will have registers that the CPU can talk to initiate SPI transactions, right? And so that SPI peripheral will have an address range. So it'll have a base address, which is the starting address, and then it'll have like a length that goes from there, or it'll just have an ending address. You guys with me? So any loads or stores in this range will essentially be a way for the CPU to target the SPI peripheral to tell it to do something on its behalf, on the CPU's behalf, right? So for example, if I asked you on a quiz, what's the size of the USP peripheral's I/O space? To figure that out, in this case, it's shown, we're showing you the starting address and the ending address. So to find the space, you would just subtract them, in this case in hex. And then you have to add 1 because this is an inclusive range, right? So this would be 1FF minus 100 plus 1 is 100 in hex, which is 256 bytes, right? Different peripherals will have different sizes of their address space, some depending on what you need to do, right? Does it make sense? Now the problem here is that all of this is initiated by the CPU. All of these programmed I/O operations have to be initiated by the CPU. So the CPU can read in the address space of these peripherals, or it can write into the address space of the peripherals. But if the peripherals want to do something on their own, they can't. There's no way for the peripheral to initiate communication with the CPU unless they use something called an interrupt, right? Which we'll talk about later. Or the CPU has to poll them. In other words, it has to keep asking it, loading from its address space and saying, are you ready yet? Did you get a packet 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 yet? And so, but all of this programmed I/O stuff, programmed I/O transactions are initiated by the CPU. Does it make sense? Now you guys seen some of this in 313, but in 313, we use the hardware abstraction layer in there, the HAL, right? The HAL was a little bit of a driver layer, basically, that hid a lot of this detail from you guys, right? So I think even when you write to the frame buffer, you used a function to write to the frame buffer, you didn't actually store into the frame buffer's address space, right? So because the FPGA guys try to hide a lot of this, they try to build software, a little thin software layer, so you don't have to directly interact with address ranges. But in embedded systems like the ESP32 and the Arduino, you may have to do that. Of course, there's drivers for these too, like Arduino libraries, right? Okay, so all right. So then the other thing you have to understand is that these control and status registers, the size of them are going to match whatever the native bit width of the processor is. So when we were using the Atmel 328P, I think it's 328P, that was an 8-bit processor. So all the loads and stores were 8 bits, and thus all the control and status registers were also 8 bits. On the ESP32, obviously they're 32, hence the name. They're all 32 bits. Now in this example, I'm showing an 8-bit one because this is a leftover example from when we're using the Atmel chip. These control and status registers are generally split into fields, bit fields, right? So in other words, you take a register that is matched to the native word size of the processor, and then it's split into fields, kind of like an instruction is. You guys remember from 212 when we looked at instructions. Instructions are 32-bit values for a 32-bit processor, and then they have different fields. It's the same thing here. So whenever you interact with these, you have to spend a significant number of instructions extracting bit fields out of these registers to read them or putting data inside these bit fields, right? So here's a contrived example I came up with. So this is a control register. It's 8 bits. The bits are labeled 7 down to 0 from most significant to least significant, in descending order from left to right. And I've got these fields. Some of these fields have names. Generally, they're all named. They have widths. So for example, bit 7 is the halt bit. Bit 6 is the on fire bit. And bits 5 down to 3 is the temp bit range, right? And then some of these are for writing and some of these are intended for reading, right? And so for example, you'll read in the data sheet, it'll say, if you want to halt the processor, you have to write a 1 into the halt field, right? So what that means is that you have to be able to write a 1 into that field. The problem is that you can't just write 1 bit, because when you do a load or store, you're loading or storing in units of 8 bits, or in the case of the ESP32, 32 bits. So in order to set a bit in a field, you have to first read the old value of the register and then somehow figure out how to get a 1 to force that 1 bit in that value to be 1, and then you have to store it back. All right? You guys with me? Likewise, if I want to read the temperature of the processor, I have to read that register and then isolate those 3 bits, 5, 4, and 3. I have to isolate those. I have to get rid of all the other bits in there to isolate those 3. And then the problem is that those 3 bits are in the middle of the register. And generally, if I want to treat that as a value and do computing with it, I have to get those bits onto the right-hand side. I have to shift them to the right. I have to right justify. I can't leave those bits in the middle because they'll be multiplied by 8, right? So if the temperature in there is, say, 4, it's not going to read as 4. It's going to read as 4 times 8 because they will have been shifted effectively to the middle of the register. So I'd want to shift those back to the right so I could justify them. You guys with me? Okay. So how does that work? How do you do that? How do you do this bit manipulation? So I don't know, you guys might have talked about this in other courses, but I remember when I used to teach 212, and I would cover shift instructions and bitwise logical instructions. Students would ask, what would you use a shift instruction for? And a bitwise logical, what's the point? No one ever uses those in 145, 146, 240, 311, 350. We don't use them. It turns out that all of those instructions you learned about in 212 that do that bit manipulation are generally used for this type of I/O, right? Manipulating control and set. They just don't tell you that, right? They just say, all right, we're learning about shift instructions today, and this is kind of what they're used for. So, for example, if I have an 8-bit, again, this is 8-bit, but this will be 32 bits on the new processor. How would I set bit 2? And when I say set, I mean I want to force bit 2 to be 1 inside that register. So first, I have to have the value in a variable, which I've called val. And then you have to have another variable called, in this case, temp, which I will initialize to 1, right? Now, you might say you don't have to physically have a variable, but this could be expressed as a sub-expression on a line of code, but this will end up being in a register when the compiler converts it to assembly code, right? So think of this like a temporary value. It could be a temporary register, temporary variable, and it'll be set to 1. And then you have to take that 1 and shift it 2 positions to the left. And the reason you're doing this, and by the way, the code for doing that is in C is less than. I don't know why we're using less thans for shifts. That makes no sense.
Looks like it moves to the left.
It looks like an arrow. Yeah, I think that's the reason why. But mathematically, that's absurd that it's less than to shift. But less than, okay, that's a shift. And so the way a shift works is that the value you're shifting is on the left part, the amount you're shifting by is on the right. So when you take that originally 1 bit and you shift it 2 bits to the left, what you're doing is you're aligning, the purpose of this is to align that 1 bit right underneath the bit that you want to set to 1 in the target variable, right? And so that 2 corresponds to bit 2, right? So my shifting by 2 because I want to target bit 2. So I do the shift, and then you, and then once you do that, you take the original value, which is val, and this temporary value, which is a 1 shifted by 2 bit positions to the left, and you do a bitwise OR, which in C is a single bar, not a double bar, right? Single bar. And remember, like in RISC-V instructions, this would be like an OR instruction, or MIPS, right? And then when you do that, all the bits that were 1 in the val would be ORed against 0 in all the bit positions except for 2, right? So all of the original bits will be retained because you're ORing with 0, except for bit 2, which is being ORed with 1, so you're forcing that to be 1. Make sense? Okay, so what that means is that you have to do quite a bit of steps to make this work. You have to get the original value that you want to set the bit in. You have to shift a placeholder bit, then you have to OR them together, and then you have to store this resultant value back. Well, what about clearing a specific bit? What happens if I want to turn a bit off, right? So for that, you have to load the original value, and again, you take a temporary value and you shift it a number of bits to the left, representing the bit you want to clear, the bit position you want to clear. So I want to clear bit 2, so I take 1 and shift it left by 2 bits. Now how do I clear it? Well, then you have to do a bitwise complement. You have to do a tilde. Again, I don't know why. That doesn't make sense. That's just weird. I wonder if, I have to look this up. I wonder if if you went to a typewriter in like 1920, if there's a tilde key on it. I wonder when the tilde even came to exist. Tilde, mathematically, a tilde means approximately, right? But it makes no sense that that's used for a complement. But anyway, this would be translated into a not instruction in RISC-V. So it's going to flip all the bits except for, well, it's going to flip all the bits, so all the bits will be 1 except for bit 2, which is now 0. And then I do a bitwise AND with that. And what that'll do is it'll AND all the bits on the original value with 1, right, which just gives you an identity operation, except for the bit I want to clear, which will be ANDed with 0, and of course it'll make it 0. Now, if that bit were already 0, it would have no effect. Just like on the previous example, if the bit were already 1, it would have no effect, right? All right. So what about isolating a specific bit, though? So, like in other words, the previous example I showed is for writing bits. What if I want to read bits? So for that, there's a few different ways to do this. So what happens if I want to read bit 3? In other words, I want to isolate just bit 3. So this is when you can use a shift instruction. So if I take that value, I can shift this value 3 bits to the right. Right? Remember, before I was shifting left, now I'm going to shift to the right. How many bits? By 3, right? That's going to take the bit I want to isolate, and it's going to put it on the right-hand side of the value, right? The problem is that I've still got a bunch of other bits garbage bits in there that I want to get rid of. And so to get rid of those, I can just simply do a bitwise AND with 1, right? Make sense? Yes?
The whole reason we have to do this is because we can only read or set a bit in the lowest position and then move it where we need it.
No, it doesn't have to be in the lowest position. This is kind of a stylistic thing. So my expectation as a programmer was that if bit 3 is set, I want the value to be 1. And if bit 3 wasn't set, I want the value to be 0, right? Now, you may not want to do that. You may instead want to do it this way. Here's another approach. If I want to isolate bit 3, I could, instead of shifting that guy right, I could just take a temporary variable, 1, and shift it 3 bits to the left, right? To align these guys like I did when I wanted to set the bit. And then I can do a bitwise AND. And that way, the result of that will either be 8 or 0, right? Now, I don't like that because I want it to be 1 or 0. This result will be 8 or 0. The result will be 8 if the bit 3 was set. It will be 0 if bit 3 wasn't set. Luckily, in C, you guys know that C and C++, I shouldn't say C++, C. In C, there is no Boolean data type. Doesn't exist. So in C, instead of Boolean, you have an integer that is either it's false when it's 0 and it's true when it's non-zero, right? Which means in C, if you treat this like a Boolean value, it will be true, right? Now, if you're in Python, or even in C++, you can actually declare something as bool, right? But this is effectively Boolean in C, right? So I don't really care that it's 8 or 0 because 8 is true in C and 0 is false in C, right? Anything non-zero is true. So if you're using an if statement for this, and what I'm trying to say is that if you're putting this result in an if statement, then it doesn't matter how you do this. If, on the other hand, you wanted to do something other than an if statement, right? You wanted to do some arithmetic, like I wanted to take that bit and multiply it by 10. Well, then I probably should get it on the right-hand side so it's a 1 or 0, right? Okay. All right, so what about multiple bits? What if I want to isolate bits 5 down to 3? Like in the previous example, this was the temperature field in my status register, control/status register, my I/O register. I had a field called temperature, which is bit 5 down to 3. How do I isolate that temperature in there? Well, there's multiple ways. One way to do it is to shift by 3 to the right. They might say, why 3? Why not 5? Well, 3, you shift by 3 because 3 is the lower limit of the field. It's 5 down to 3. So you're going to shift by 3. And once you do that, you want to isolate bits 2, 1, and 0. Why 2? Well, because 2 is 5 minus 3. So so if it's n down to if it's m down to n, m comes first. Yeah, if m down to n, you shift by n, and then you're going to mask off m minus n bits, right? Plus 1. Sorry, that's 3 bits, right? 5 down to 3. 3, 4. 5, 4, 3. 3 bits, right? N minus n plus 1 is the number of bits. So I'm going to shift it by the lower limit, which is 3. I'm going to shift it, and then I want to mask off 3 bits. How do you mask off 3 bits in C? Well, it's actually kind of hard to do that. One way to do it is, the way I like to do it, is I like to take 1, shift it by 3, because I want 3 bits, right? And then subtract 1. So if you take 1 and you shift it by 3 bits, you get 8. But then if you subtract 1, you get 7, which is 1, 1, 1, 3 bits, right? That's one way to do it. Now, it turns out that the nice thing about this is that 3 could then be a 4, and you'll get 4 bits, or you can put a 5. This becomes an expression that becomes kind of flexible, right? You can plug in whatever value you want here, and you'll get that many 1 bits out of it. But in in C, I have to remember how this works. In ANSI C, there's multiple C's. There's ANSI C and there's C99. One of them, I think it's ANSI C, allows you to have binary literals. A literal is just a number. So you can do a binary literal, which is 0B111. But that's not technically part of the C language. That's a hack. You're not supposed to be able to do that. But they did that in ANSI C. But in strict C99, you're not allowed to do binary literals. But luckily, I think all the compilers I've ever used supports that binary literal, right? But if you put the literal in, you can't. You're stuck at 3-bit 111, right? But if you do it this way, if you say 1 shifted by 3 minus 1, then you can have that'll substitute for as many bits as you want, 1 bits, right? So the idea is that I'm going to shift this by 3 bits to the right, and then I'm going to AND it with 3 1 bits aligned on the right-hand side, which I can do with 1 shifted by 3 minus 1. So I do the AND, and that way I isolate the temperature field, and I also justify it as well in the result. Okay. Okay. When are we done? 11:20? Okay. All right. So yeah. So here's another example. There's the 0B111. So you remember a hexadecimal number is 0x, right? You start with 0x. If you put a 0B, it's a binary, and then there's octal. What's octal? 0O, or is it just 0? I don't remember. But you can also do octal literals, but I've never seen anyone use an octal literal. Octal is 3-bit value. Okay, so right. So or what if okay, so that's for reading. I showed you an example for reading. This was reading those 3 bits. What if I want to write those 3 bits? How do I do that? Well, this one is probably the hardest one, because the problem is that when you write a single bit, you use the OR, the bitwise OR, right? But you can't use the bitwise OR directly on here, because the problem is if I want to write, say I want to write 4 in here, 100, right? If I just do a bitwise OR with 100, it's not going to put 4 in here. I'll end up getting 7, right? Because it's not going to set these 2 other bits to 0, right? So the problem with this, whenever you set a multi-bit value, you have to, maybe there's a better way to do this, but the way I've always done it is you have to clear those bits first, and then you OR in the value that you want to insert in there, right? I don't know of any other way to do it. Well, there is another way with structures, which I'll talk about in a minute, but doing it at a low level. So the way I do it is I take 1 shifted by 3, y3, because 3 bits, subtract 1, that gives me 111, and then I shift it 3 bits to the left. So now we're having to go through 3 different operations here, right? Number 1, I have to set up my 3 bits, my 3 1s. So that's 1 shifted by 3 minus 1. Then I have to position that underneath that field, so I have to shift that value by 3 bits to the left, right? That way I get those 3 bits are aligned under the temperature field properly, right? Then you have to negate that, right? So you have to flip all the bits. Then you have to AND. So you AND with that, which clears the original temperature field out, right? And then you have to take your new value, which if it's 4, I represented 4 here in binary, so 0B111. Shift that by 3, get it into the position, and then you do your OR operation to insert the value. So that's pretty awful. The bigger problem is, this is where I always run into trouble. Let's back up here a minute. Take a look at this expression. One of the issues with this is that I don't have parentheses around all of the pieces of this. I have some parentheses, but not a lot. Now, when you do normal mathematical operations, everyone knows that multiply and divide have a higher level of precedence than add and subtract, right? You learn that in grade school, and if you want to do the add and subtract before the multiply, you use parentheses, right? The problem is now we're mixing shift, bitwise logical, and add and subtract all in one expression. If these things are not evaluated in exactly the order that you intend them to be evaluated in, this will fail horribly, but you won't even know it. Okay, I want to mention something else here too. One of the reasons I dumped the Arduino boards is that there's no debugging. You can't debug. But by debug, I mean set a breakpoint in your code, run it until that breakpoint, and then have the ability to inspect the state of your code, right? You guys use debuggers? When I learned about debugging, I think I was in grad school, because they didn't teach it when I went to undergrad. And they don't teach them here either, I don't think. When I learned about debuggers, that was huge. That revolutionized the way that I coded, right? The fact that I could use debugging to very quickly identify and fix bugs in the code without having to do print debugging, which is terrible. Because you guys print debug, you got to put prints, and you have to recompile and run it and put other prints in and then go back and remove the prints. It's terrible. It's a really bad way to debug. Using a debugger like GDB or the one that's built into Eclipse or Visual Studio is awesome. There's no debugging with Arduino. And the reason is because in order to do debugging, you need special hardware, and no one has that hardware ever. You need a debugging module, right? With the FPGAs in 3.13, we had debugging support. We could debug, right? Well, I use that a lot. Now we don't have debugging. Now we're going back to this ESP32, no debugger, right? So the issue is that if this expression is evaluated in the wrong order, you're not going to know. Your code's just not going to work. And it's really hard to figure out, like, how are you going to know? How are you going to know that the bug is from the evaluation order being wrong, right? That's tough. I don't really have a good solution for that. I mean, you can print, like you can do your operation on the control register and then print the control register, but then it's in hex. So how do you can't, as a human, you just see a hex, like you don't know the temperature, like this temperature field doesn't even fall on the hexadecimal boundary because it's 5 down to 3. These numbers aren't divisible by 4. So this doesn't even correspond to a hex number inside of a hexadecimal value. Very difficult to debug this, right? Another way to do it is you can write the control register and then read it back and confirm that what you wrote went through correctly, right? But you have to be very careful. I just want to caution you that this always bites me. To be very careful with these when you start combining these things into complex expressions, because it's not obvious what the order of operations is here. Now, as it turns out, I mean, you can look it up, what it is. Let me fast forward a bit. So it turns out that the tilde has the highest priority. Why? I don't know. Then add and subtract, evaluated from left to right, and then shifts, and then logical bitwise at the bottom. It's like, wait a minute, wait, tilde is a logical bitwise. Why is tilde the highest priority thing you can do, and or the lowest priority? That doesn't make any sense. That's just the way it's set up in the language, right? So what ends up happening here is if I put an expression like this, so I want to set, basically what I want to do here is I want to set a 3-bit field that's bits 11, 12, and 13. 13 down to 3, right? I want to set that field, and I want to set it as F, right? So I want to put the value F into bits, what is it, 13 down to 11. 13 down to 11, right? I should have wrote that there, sorry. Yeah, I want to set a 3-bit field whose least significant bit is bit 11, right? So you could do something like this. You can say, you take the register value, the old value, and I need to clear those bits. So to clear those bits, I'm going to take 3 I'm going to take 1 shifted by 3, right? Subtract 1, that gives me 1, 1, 1, right? Shift that 11 bits to the left, right? Then complement that, right? Then AND that to clear it, right? And then OR F shifted by 11 bits in, right? So this one line of code will take the value of F and we'll put it into a bit field that is 11, 12, and 13. Bits 11, 12, and 13, right? The problem is it's not going to work because if you look at the order, the evaluation order, the tilde happens first, but that's not what I wanted. I wanted to take 1, shift it by 3, subtract 1, and then complement, right? But that's not what's going to happen. What's going to happen is I'm going to tilde first. So I'm going to take 1 and complement the 1, right? Then I'm going to subtract 3 minus 1. So this 3 minus 1 will become a 2, right? So then I'm going to take the complemented 1 and shift it by 2 bits to the left, right? Then I'm going to shift that result of that by 11. And then I'm going to shift F by 11, and then I'm going to OR everything together, which will be a mess, right? So we have to make sure that we use parentheses here very carefully to make sure that the evaluation order is correct. Now, of course, the problem is that when you have something like this, you could use too many parentheses and make it unreadable, right? So this is the minimal number of parentheses, I believe, if I didn't screw this up. So we have 1 shifted by 3 bits, then subtract 1. So I did not need parentheses with the minus because that was good. The minus is good. But I did need parentheses with the left shift by 11. And then I was okay here. I didn't need parentheses with this F shifted by 11, and I didn't need anything here, right? So this is the correct statement. You guys with me? All right, so just be aware of that. Okay, so let me back up here again. Okay, so here's just a summary. Set bit 1 is shift by n bits, or set bit to 0, shift by n, take a 1 shifted by n bits, complement and, right? Isolate or extract or read bits n down to m. I should have went m and n. I don't know. Yeah, anyway, this is n down to m. It should be m down to n, but anyway. But the code is correct. So I'm going to take the value and shift it by m, which is the least significant part, right? And then I'm going to AND it with n minus m plus 1, which is the number of bits of that field. Shift that to the left, subtract 1, and then AND it together, right? You guys with me? So this will isolate bits n down to m and then also right justify them. And then if I want to just isolate a flag, like if I don't care about right justifying, I just want to check to see if one of the bits is set and and then treat that like a C Boolean variable, which is not really Boolean, it's like 0 or non-zero. Then I can take 1 shifted by n and then just do my AND and use it as part of the if statement. You guys with me? All right. Okay, so now the question is, I've talked about how to manipulate the bits, but I haven't talked about how you physically move data between the control registers, right? So this is something that actually depends on what platform you're using. So if you think about the way C is set up, and you guys haven't actually taken a lot of, you only took 240 was your only exposure to C pointers, right? So in C and C++, you have this notion of a pointer, which is basically just an address, right? It's a memory address. And to go along with that, you have the star operator, which is called a dereference operator. So if you have a pointer and you put a star in front of it, that dereferences it. And if you have that dereference on the right-hand side of an assignment, it becomes a load instruction. And if it's on the left-hand side of an assignment, it becomes a store instruction. So what I mean by that is, if I have now the other thing that's confusing, at least I always found this confusing, is that when you declare a pointer, you also use the star. But this star in the declaration is not a dereference. This star means something else. This star means you're declaring a pointer, right? But then use the star later on, and that is totally different. So I always found that to be really confusing about C, which is, why do you have to put a star when you declare it, but then, the star means something else when you in context. But anyway, in this case, I have the peripheral address, or the starting address of the peripheral. This is the base address at 100. You guys with me? This is where the addresses start for that peripheral. And I've set them up as a define. And then I have an offset. So this offset is how many bytes after that starting address of this specific control register I want, right? Now you might say, well, that's asinine. Why not just list the addresses for each register? You could, but if you read the ESP32 technical reference manual, they actually use this format where they'll say they'll have control registers with just offsets associated, not absolute addresses, but relative addresses, right? Which it kind of stinks because then you have to do the math to figure out where the actual address is, right? So what's happening is that this USB is an IP block inside the system on chip. It's a circuit, and it has a starting address, and then that starting address may have multiple control registers, which then have offsets. Okay, so then what you'll do is declare a pointer, which is PNTLS, right? And that's going to be the USB address plus the offset. So this is the effective address of that register. Okay? Now you might say, well, wait a second. You're adding two, these are integer literals. You're adding two literals to get a pointer, and the compiler going to be upset about that? No, actually it's fine with that, strangely. You know, you don't have to typecast these things as pointers. You just add two integers and you can assign it to a pointer, and compilers typically fine with doing that, right? Now notice these are all magic addresses. You're not supposed to use magic numbers in your code, but these I/O addresses are the one exception to that rule because, like I said, they're baked into the hardware. They literally can't change. So it's okay to make magic numbers here. Magic numbers anywhere else in your code isn't good. Okay, so then one option is you can take this pointer and dereference it to read it, right? Now here's the problem with that. That's actually the way it worked in the Arduino, the Atmel chips, right? But in other architectures that have a cache, there's an issue because if you dereference an I/O address as a regular load or store instruction, that may get intercepted by the cache because the hardware may think that you're accessing memory, right? But whenever you access peripherals, you want to bypass the cache, right? So the way that's done, and I don't actually know how ESP32 does it, but on the FPGA boards that we use in 313 and 611, or at least I should say on the Neos processor that we put on those FPGA boards, there's a special variant of the load and store instruction for doing IOs. They have load IO and store IO. The purpose of those is to bypass the cache, right? But how does the compiler know you want to use that it should generate the load IO versus the load instruction? Generally, it knows that through this thing called volatile. You see that volatile keyword? So if you declare a pointer in C as volatile, it doesn't mean anything for the language, the C language, but the compiler will look at that and say, okay, if he declared this pointer as volatile, he probably intended this as an I/O instruction, an I/O load. So I'll bypass the cache. Because otherwise, if you don't bypass the cache, you try to write into a peripheral, and the peripheral never sees the value you wrote because it got caught in the cache, right? It got the cache, you cache the value instead of actually sending it to the peripheral. Okay, so, but in order to avoid all this issue, typically you'll have a macro to do this. So notice there's something called reg read, right? So if you use reg read with the address, it'll just essentially act as a dereference, but it'll ensure that it gets generated properly in the code. So the you guys probably remember the Neos processor had a similar thing. It was called IO read 32, IO write 32, right? You might have used those in 313. In the ESP32, we've got these reg read, and there's also a reg write, right? Make sense? All right. So okay, so we talked about that, and yeah. So this is, like I said, the most common sense way is to read with a dereference of a pointer on the right hand side, and to store your dereference on the left. But you should probably avoid this and just use the macros that are provided, right? The reg read and reg write instead, which are shown here, right? We got reg read and reg write. And then there's also macros for setting and clearing individual bits. So in order to do that, you would say reg set bit, the value that you want to set. Actually, this would be the address. That's actually wrong. That should say address. Sorry, not value. That's the address. Okay, so that's the address, and you would still have to shift the bit you want to set, or shift the bits you want to clear, right? Now you might say, what's the point? I mean, it's just as easy just to use the code that you showed us earlier. Well, no, because actually this set and clear also take care of reading the old value. It reads the old value, then it sets and clears the bits, and then stores that value back. So it takes care of a lot of that stuff for you. It simplifies the code, right? Otherwise, you would have to read the old value, set the bit or clear the bit, and then store it back. So this does both for you in one shot, right? Okay, and then I'm going to skip that for now, actually. Okay, so let me, do I have time? Let me run through a really quick example that's concrete. And we'll be revisiting this later when we talk about the ESP32. But I want to show you an actual example of when you have to do this that's not some made up stupid thing I came up with. So the ESP32 has 48 physical pins on it. 8 of those are power and ground and clock pins that you can't touch. They're hard. They have specific purposes. But 40 of them are essentially user configurable, kind of like on an FPGA where you have I/O pins, user I/O pins on an FPGA. You can use those pins for reading or writing or whatever you want to do with them. So you have these 40 pins. The problem is how do you set up those pins to have them do what you want them to do? So they have this system set up, and the Atmel chips have a similar system. Every one of the physical pins, every one of the 40 pins, has a control register associated with it. And that control register controls a mux that allows you to take any of, so there's 173 internal signals inside the chip that could be used as inputs. And there's 190 internal signals that can be used as outputs. Right? So there's 173 things in the chip associated with different peripherals and stuff in the system on chip that can be written to, and 190 that can be read from. And so if you want to take any of these signals and attach them to any of the 40 pins, you have to set up this mux. It's called a GPIO matrix. And so there's one of these for input and there's one of these for output. But I'm going to show the output one first. So you've got this mux, and you have to set a control register for a specific pin. So for instance, what you could do is you could take, and I've done this before, you can take all 40 pins and have them attached to the same signal. So you can have the same one of these signals and broadcast it out to all 40 pins and just have them all act the same way, right? Because it's a matrix. It's a full crossbar in the sense that you have a mux for every output, right? But there's a separate control signal for each one of those mux. But then to add a little bit more complexity, there's a second mux after that that's used to disregard the first mux if you want to, right? To short circuit it, right? So in order to set up an output pin, you have to set both of these muxes up. That's my point, right? And to do that, there's a separate control register for each, okay? So let me just show you what that looks like. So these are the two registers. So for example, for pin 12, there's something called GPIO func12 out select config reg. And then that's the first mux. And the second mux is called IO mux, GPIO 12 reg. Now notice that these are 32 bits, unlike the 8-bit ones I showed in the examples. And also you'll notice that a lot of these registers have bit fields that are just, they're marked reserved, meaning that you're not supposed to write to them, and you're not supposed to read from them and interpret them in any way either. They're just reserved. So, and that happens a lot when you have 32 bits. Like in the Arduino, the Atmel, the ATmega 328, because there were 8-bit registers, there wasn't a lot of reserve bits in there. But in the 32-bit processors, there tend to be a lot of reserve bits. So basically, in this case, it's 9 bits. The function is 9 bits. So I can select any of the internal signals and route them out by selecting this 9-bit. And there's a big table in the reference manual, which is linked on Blackboard, by the way. There's a link to the reference manual. There's a table with what all these codes are. And then the other mux is, the I/O mux has a little 3-bit field over here that you have to set, right? The problem is all 40 pins have a different interpretation of what the I/O mux select does. So then there's another table in the technical manual that you have to look up for each of those pins. So depending on what pin you want to set up, you have to look up its specific I/O mux setup. You guys with me? So this is an example of how you would have to write code to set these fields to achieve a certain goal. All right, I guess I'm out of time, right? Yep. So I'll see you guys on Thursday.